Welcome to Math Mondays. I'm Miss Barnes, and this segment is for kindergarten through second grade. Friends, today we're going to be working with a strategy that requires a 10 frame. Do you remember what a 10 frame looks like? It's just a table that has 5 columns and 2 rows. If you don't have one at home, I'm going to show you a really quick way to make one. But you don't even need a 10 frame as long as you can organize your counters or your chips or your action figures into 2 rows of 5. Okay? But I'm going to take my piece of paper and find my marker, and I'm going to fold the piece of paper in half long lengthwise so that I'm folding the paper like a hot dog fold. And then I'm going to draw a horizontal line, and as best you can, I want you to try and draw 5 even columns. Mine are almost even, but they're not quite. So if yours are not quite even, that's okay. All right, here is my completed 10 frame. You're going to need one of these for our lesson today. So take a minute now, and let's get ready to learn. All right, our objective this morning is I can use a 10 frame in order to solve problems. And we are going to be working with the 10 frame, which hopefully you made. Today we're just going to be using red counters, and you might want a piece of paper and a pencil or writing utensil. Ready to get started? Here's our first question. Now remember, we have to read the whole question before we can start to solve. That way we understand the context or the story behind the problem. So let's read the problem here. A team has 5 soccer balls at their practice. The coach brings 2 more balls. How many soccer balls does the team have now? Model the problem using the 10 frame, then write an addition sentence to solve. All right, so tell me the story behind this problem. So we're at soccer practice, and the team has 5 balls that they're using to practice with. How do we model that? Remember, on our 10 frame, we can add 1 counter to the 10 frame as we count in order to organize our information. Let's do that now. So here's 1 counter, 2, 3, 4, 5. So that's modeling the first sentence. A team has 5 soccer balls at their practice. What does the second sentence say? The coach brings 2 more balls. How do we model that on our 10 frame? Let's just add 2 more counters to our 10 frame. 1, 2. How many soccer balls does the team have now? All right, so the next thing we need to do is we need to write a sentence that will answer our question. So here I'm going to write, the team has blank soccer balls. And remember that that blank there just tells us we haven't yet solved our problem. Okay. Now we have to write a number sentence that solves our 10 frame and the model. So what do we do first? Well, we look at the first row and we say, how many counters are in the first row of the table? Well, we know that a full row on a 10 frame means that there are 5 counters. We're going to go ahead and count them individually to make sure. 1, 2, 3, 4, and 5. So in one full row of a 10 frame, there are 5 counters. Whoops, I'm going to undo that and try again. 5 counters. Now we have to count the number of red counters in the second row. How many are in the second row? 1, 2. So I'm going to add that to my number sentence. 5 plus 2. Now I'm going to do some erasing. And I want you to think back to a strategy you know that can help you get to the answer. Do you remember how to count on a number? So we're going to start at 5 because we know that 5 counters fit in the first row of the table. And now we're going to count on 5 in order to get our answer. So using our counters, we have 5 in the first row. What comes after 5? That's right, 6 and 7. So what's 5 plus 2? That's right, 5 plus 2 equals 7. That means the team has 7 soccer balls. Great job. Are you ready for number 2? All right. So here's our second problem that we're going to do together today. We're going to read the whole problem first. Leah reads 4 books. Her friend Kennedy reads 5 books. How many books did both girls read? Model the problem using the 10 frame, then write an addition sentence to solve. All right, it's your turn. Tell me what to do first. That's right. First, I should write a sentence that answers the question to my word problem. So the question is, how many books did both girls read? So think about it for a second. What would you write as a sentence to answer that question? I would write, both girls read books. Both girls read blank books. And always remember that that blank just means we haven't solved for the total yet. Now, we need to go back and we need to read sentence by sentence in order to organize our information. So, Leah reads 4 books. Let's stop there. Leah reads 4 books. Now, using the 10 frame, how can we model this? That's right. On the first row of the 10 frame, we are going to add 4 counters. 1, 2, 3, and 4. Let's read the next sentence. The next sentence says, her friend Kennedy reads 5 books. And we'll stop there. How do we model this on our 10 frame? That's right. On the second row, we're going to add 5 counters. 1, 2, 3, 4, and 5. So this 10 frame models our word problem just as we read it. Now the next step is we need to write an addition sentence to solve our problem. So do you remember how to do that? What do we do first? That's right, we count the number of counters on the first row of our table. So count them with me. 1, 2, 3, 4. So the first number in our addition sentence is going to be 4. Now, you're probably going to say that the next step is to count the number of counters on the second row. But I want you to remember what we know about a 10 frame. If the row is full, how many counters are on it? That's right. If the row is full, just like this second row, that means we have 5 in our 10 frame in that row. So the second number here is going to be 5. Now the next thing we're going to do might confuse you a little bit, so make sure you listen really well. We're going to count the number of counters in our 10 frame, but we're going to start with the number 5 because we know this second row has 5 in it. So starting with 5 and then counting on 4 more. Are you ready? So for the bottom row has 5. So this one is 6. The next one is 7. Then 8. And last we have 9. So what is 4 plus 5? That's right, 4 plus 5 is 9. That means together, both girls read 9 books. Really, really, really great job. There's one more problem that we're going to solve today, and that problem is right here. So let's read the whole problem from start to finish, and then we'll go back and solve each sentence. Justin packed boxes over the weekend. He packed 3 boxes in his kitchen, then 5 boxes in his living room. How many boxes did Justin pack? So remember, the first thing I want to do is write a sentence to answer the question. So my sentence will be Justin packed some boxes. And we'll fill that blank in just a second. Now we're going to go back and read the problem sentence by sentence. The first sentence says, Justin packed boxes over the weekend. Stop there. Does that sentence give us any information about the problem? No, not really. So let's continue. He packed 3 boxes in his kitchen, then 5 boxes in his living room. And that's where the period is, so that's where we'll stop. I'm going to break this sentence down into 2 smaller chunks. The first one says, he packed 3 boxes in his kitchen. So how do we model that? That's right, let's put 3 on the first row. 1, 2, 3. The second half of the sentence says, then 5 boxes in his living room. So how many do we need to put on the second row of the 10 frame? That's right, we need to put 5 on the second row of the 10 frame. Next, we need to add a number sentence to our work here. So let's talk about the first number. How many counters are on the first row of the 10 frame? That's right, 3 counters. And on the second row, we know there are 5 counters. And can you tell me what 3 plus 5 is? That's right, 3 plus 5 equals 8. So Justin packed 8 boxes. Great job today, friends. That was a lot of really hard work. It was my pleasure to have you in class today, and I'll see you next week.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.
To KCPS Homeroom Math Monday. I am so excited you joined me today. As you know, I am Erin Dorsey, and I am one of the math curriculum coordinators for Kansas City Public Schools. Today, we're going to learn all about how to find and calculate perimeter. Have you heard the word perimeter before? Well, let me give you a little bit of a hint. Come with me into my backyard. Welcome to my backyard. As I turn to my right, you're going to notice something along the side of my yard. Do you see what I see? If you see the fence then you are looking at an example of perimeter. Well, perimeter is the distance around an object. So when you have a fence in your backyard, that goes around your entire backyard. The distance around your backyard is where the fence goes. So in order to build the fence and make sure that you have enough fencing for your yard, you have to calculate the total distance around your yard. That's a perfect example of perimeter. Can you think of some other places where you would have to calculate perimeter? That's right. What if you are in your house and you are cleaning around the baseboards? Your parents ever make you do that? I make my kids do that. They always want to make sure that they get the smallest room so they can do the least amount of work. So they're going to want the one that has the smallest perimeter, smallest distance around the room, so they do the least amount of work. Can you think of any other examples? Go ahead, shout them out. There are fences at basketball courts, distance around playgrounds. All of that is perimeter. What if you wanted to create a flower bed where you planted flowers and you wanted to enclose that area? You would need to calculate the distance around that flower bed to know how much material you needed to enclose that flower bed. Now, let's take a look at some shapes and calculate their perimeter. Come on, let's check it out. Perimeter is the distance around an object. So if I wanted to find the perimeter of this blue square, I would want to calculate the distance around the object, or the sum of all the object's sides. Remember, the word sum is the answer to an addition problem. So to find perimeter, you would add up all the sides. Now let's take a look at this blue square. What do we know about sides of a square? That's right. The sides of a square are all equal. So side lengths are the same. So if I wanted to find the perimeter of this blue square, and the lengths of each side was 12 feet, that means that all four sides measure 12 feet. If perimeter is the sum of all the sides, what am I going to have to do with the length of each side to find the perimeter? That's right. I'm going to have to add them together. 12 plus 12 is 24. 12 plus 12 is 24. When I add 24 and 24, I get 48 feet for the perimeter of this square. Let's check out this rectangle. A rectangle is different from a square in that not all sides are equal. However, corresponding sides are. Let's take a look at this. This side is equal to this side, and this side is equal to this side. So if I know the length of one of them, let's say this is 6 inches, I also know the length of the corresponding side. So if the length of this side were 13 inches, I would know the length of this corresponding side. To find the perimeter of this rectangle, what would I do? That's right, I would add them all together. So I have 6 plus 13 plus 6 plus 13. 6 plus 13 is 19, and 6 plus 13 is 19. If I add 19 plus 19, I get 38 inches. So the perimeter of this green rectangle is 38 inches. Let's take a look at the next figure. Here we have a triangle. In this triangle, I have two sides with a length of 20. Oops, let me get the pen back again. The laser's not going to work, it disappears. I have two sides with a length of 20 yards. And I have one side with a length of 30 yards. How am I going to find the perimeter, the distance around the triangle? You got it, I'm going to add. So let's add these sides together. 20 plus 20 plus 30. 20 plus 20 is 40. 40 plus 30 is 70 yards. The perimeter of the red triangle is 70 yards. Let's take a look at these two objects. The first one is a dining room table. If I wanted to find the perimeter of the dining room table, what information do I need to know? Absolutely, I need to know the lengths of each side. So let's say that the length of the longest side is 8 feet. And the length of the shorter side is 3 feet. How can I use these numbers to help me find the perimeter of the table? I'll give you a hint. Remember, corresponding sides of a rectangle will have the same measure. That's right, I'm going to add them up. If I know that the length of the longer side is 8 feet, I also know the other side is 8 feet as well. If I know the length of the shorter side is 3 feet, then that means the length of this short side is also 3 feet. To find the perimeter, what am I going to do? Add them all up. So I have 3 plus 8 plus 3 plus 8. 3 plus 8 is 11. 3 plus 8 is 11. 11 plus 11 is 22, and my unit is feet. So that means that the perimeter of the rectangular dining room table is 22 feet. You guys are great at this. Let's take a look now at the flower bed. What happens if I know the perimeter, but I don't necessarily have all of the dimensions? So let's say that the distance around this flower bed was 64 feet. That is the perimeter of the flower bed. And this flower bed is a square flower bed. Remember what we said about squares? That's right, all sides of a square are equal. Since a square has 4 equal sides, I know that they're going to have the same measure. If the total is equal to 64, that means that I could take 64 total feet and divide it by the amount of sides in the square, which is 4. And what am I going to get? Well, 64 divided by 4 is 16. That means that the length of each side of this flower bed is 16 feet. And I can check my answer by adding up the sum of those sides. 16 plus 16 plus 16 plus 16. 16 plus 16 is 32. 32 plus 32 equals 64. That checks out. Great job, guys.
Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything.
We are Southeast.
Southeast.
We stand shoulder to shoulder.
Join the Southeast family. Enroll today.
I chose manual because it's challenging and fun and it can help me with college.
I chose manual because I wanted to get a jump start in my career with culinary arts.
I chose manual to acquire skills I'd use in real life.
I chose manual because I want to be an ER doctor and be an EMT is my first step.
Kickstart your future today at Manual Career and Technical Center. Manual is open for all 11th and 12th grade students in both Kansas and Missouri. Learn more today at enrollkc.org/manual or call 816-418-5200.
My name is Mary Jo Fender, and this is Math for Middle School. Today we're going to continue our work with exponents, and our goal today is to use a power to a power property and the power to a product property to simplify expressions that have integer exponents. What you'll need today is paper and pencil. Okay, take a few seconds to get ready to learn. In our first example, we're going to use our product of powers property to illustrate how to find powers of a power. Now in our first example, 6 to the 4th power to the 3rd power, you'll notice we have two exponents. I want you to focus on the exponent that is outside the parentheses, the 3. That tells us that our 6 to the 4th power is actually working as a base. And our product of powers says if we can expand that out, and it looks like this, 6 to the 4th power times 6 to the 4th power times 6 to the 4th power. And we have the same base, we simply have to add our exponents. So it would be 6 to the 4th plus 4 plus 4. 4 plus 4 plus 4 is 12. So our simplified version of 6 to the 4th to the 3rd would be 6 to the 12th. Now, using the product of powers property, can you see a shortcut for powers of a power? Is there another way we could get 6 to the 12th by looking at our original expression? If you said yes, hang on to that thought. Let's do another one and see if your guess works out for our second example. Our second example is 2 to the 3rd to the 5th. Now, if we expand that out, remember our 5 is going to tell us how many times to write our base. And our base is inside the parentheses, the 2 to the 3rd power. So in expanded form, it would be 2 to the third times 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 2 to the third. Now remember, product of a power, we can simply add our exponents if we have the same base. We have the same base of 2, so that would look like 2 to the power of 3 plus 3 plus 3 plus 3 plus 3. If you add all of those exponents together, you would get 2 to the 15th power. If you look back at our original expression, is there another way you could get 15? If you said yes, and you notice that 3 times 5 is 15, you have figured out how to use the power to a power property. The power to the power property says if we have a power to another power and it has the same base, which in case this does, we simply multiply our exponents to get our simplified form. Let's take a look at what that would actually look like in algebraic terms, in numbers, and in words. If you notice, our algebraic expression is a to the m to the n. We have the same base. You simply multiply m times n, and whatever that product is your new exponent. Sometimes it's a little bit easier to see in numbers. We have 5 to the second power to the third power. We're working with the same base, so simply multiply 2 times 3. 2 times 3 is 6. That is our simplified version, 5 to the 6th. Now in words, it's going to sound something like this. To find the power of a power, multiply the exponents. Let's take a look at another example. This time we're going to throw in a power of a product. You'll notice this time we have a coefficient of 2 in front of our variable power. So our base is actually 2 times a to the second power. Now the 4 is going to tell us how many times we're going to multiply that particular factor, and how that would look would be something like this. 2 to the a to the second times 2 to the a to the second times 2a to the second times 2a to the second. That gets kind of repetitive and hard to say, kind of like a tongue twister. If we expand that even further, we can actually see how the property is actually created. If we break it apart, notice we went from 4 terms to 8 terms, because when we have a coefficient in front of a variable, like it is in our example, that means to multiply. So when we break it apart, we're saying 2 times a to the second power times 2 times a to the second power times 2a to the second power times 2a to the second power. If I rely on some of my other properties, I can say commutative property allows me to group like bases together, like coefficients as well. So I'm going to move all my coefficients of 2 to the front, and I'm going to move all my variable powers to the back. Now when you notice that, I'm going to rewrite them as a power, so I can use my power to a power property to simplify my variable power. Now you'll notice I have 4 2's, and another way to write that would be 2 to the 4th power. You'll notice I also have 4a to the second powers, so I would rewrite that as a to the second, don't forget your parentheses, to the 4th power. Now that's called the definition of powers. I'm just rewriting what I've known in expanded form as a power, so I can use my other powers of exponents to simplify. Now 2 to the 4th power is 16. Now when we have a to the second to the 4th power, we're going to multiply the 2 and the 4 to get our 8. This is called the power of power property. When we are ready to write it in our final form, we're going to take the multiplication sign out and it's going to look like this: 16a to the 8th. How it would look like as a power to a product property in algebra is going to look something like this. We're going to say a times b to the m. Notice the m is being applied to both the a and the b. In numbers, it's going to look similar to this: 2x to the 3rd to the 4th. The coefficient of 2 also has a power of 4. X to the 3rd also has a power of 4. So we're going to figure out the product of 2 to the 4th power, that happens to be 16. I'm going to use my power to a power property for x to the 3rd times 4. That's going to be x to the 12th. So my final simplified answer is going to be 16x to the 12th. Now how that sounds like what that sounds like in words is something like this. To find the power of a product, find the power of each factor and multiply. Let's take a look at another example. If I have 6x to the 2nd power, you'll notice that my coefficient does not have an exponent. We need to remember that there's an imaginary 1 there. And when we apply the exponent of 2 that's outside the parentheses, we're going to say 6 to the 2nd power times x to the 2nd power to the 2nd power. The explanation for that would be a power of a product property. We're going to then continue. I'm just going to bring down my 6 to the 2nd power. I'll evaluate that in just a minute, but I want you to make sure you notice on the variable power I'm saying x to the 2nd times 2. Our next line would be our evaluation of our 6 to the 2nd power, and that would be 6 times 6. Now we're also going to do x to the 2nd times 2, so that would be x to the 4th. So our simplified answer for 6x to the 2nd power would be 36x to the 4th. We have time for one more practice problem. Negative 2x to the 4th to the 2nd power. Now, a couple of things I want you to notice. The 2 is a negative, so we're going to have to be careful when we apply our power of a product property that we make sure that negative 2 is in parentheses. So let's take a look at how that would look. So when I apply the power of a product property, I'm going to say negative 2 to the 2nd power times x to the 4th times the 2nd power. Each of my factors are now in parentheses. My power of a power property says I'm going to work with my variable power first. Because I have two exponents, I'm going to multiply those exponents together. So 4 times 2 is going to be 8. So my exponent on my x is going to be to the 8th power. I'm now ready to work with my negative 2. My negative 2 is to the 2nd power, so that means negative 2 times negative 2, that is equal to 4. So my final simplified form is 4x to the 8th. That concludes our lesson for this week. I'd like to take a quick review with you. The two properties that we've learned today have been a power to a power property and a power to a product property. A power to a power property says to just simply multiply your exponents. Power to a product property says find the power of each factor and then multiply. I'd like to remind you to make sure that you practice your math this week so you can continue to improve. It's been my pleasure to have you in class today. My name is Mary Jo Fender, and I'll see you next week.
kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.
To Math Monday. Our lesson for today is describing the effects of parameter changes or transformations on the graph of parent functions. Before we start, please be ready with your supplies. You will need your pen, your notebook, and get ready with your devices also, as we will be using the Desmos graphing calculator to graph functions. So let's start with linear functions. So we will consider the linear function y is equal to mx plus b, where b is 0 here, and our parent function when m is equal to 1. So the equation y is equal to x is our reference graph. We will call this as our parent function. The value of m is 1, and that is the coefficient of x. And we are going to compare this to the equation y equals 4x and the corresponding graph. In this case, our m, or the slope m, which is the coefficient of x, is equal to 4. And also, when y is equal to negative 2x, when m is equal to negative 2. So if we have the parent function y is equal to x, okay, y is equal to x, so we have this blue line here. It passes through the origin, and when your x is 0, y is 0. When x is 2, y is also equal to 2, so that explains the equation here that describes the equation y is equal to x. X is 4, y is 4. That's the point here. Now, compare this to the graph of y is equal to 4x. This red line represents the graph of y is equal to 4x. So what happens to the graph when we increase the value of m, or the slope m, from 1 to 4? Okay, write down your answer on your notebook, or let's see how your answer compares to mine. Okay, so if we have y is equal to x, notice that the line here, y is equal to x, compared to the line y is equal to 4x, in terms of steepness, okay, y is equal to x is flatter compared to y equals 4x. So as you increase the value of the slope m, the line becomes steeper and approaches the y-axis. It approaches this y-axis. Okay, it becomes steeper. And if we compare these two graphs, both of them have positive slopes. We compare this to the line whose slope is negative. Okay, so the first two lines, notice that as x increases, y is also increasing also. So this is the case when the line is rising. Okay, this is inclined to the right, Same here, when x, as the value of x increases, y also increases. But this is not the same case when we have a negative slope. Okay, in this green line, which represents the equation y equals negative 2x, the line is inclined to the left. Okay, so if you have a line whose slope is negative, the line is falling. Okay, falling because as your x increases, notice that as we move from left to right, the value of y decreases. Again, if we compare this to graphs 1 and 2, these two lines here, these two lines are rising. And the line with a negative slope, the line is falling. Okay, I'll give you time to process. You can take down notes. Then let's move on by graphing all these three lines in one coordinate plane. So going back, this blue line in the earlier slide, in the previous slide, is y equals x. Then the red line, y is equal to 4x. Notice the effect. When we changed the value of m equals 1 to m equals 4, this line here moves closer actually to the y-axis. So as we increase the value of m, the line becomes steeper. Okay, and both these two lines have positive slopes and they're both rising. They're both inclined to the right. And the green line, which we showed earlier, this is the line y equals negative 2x. It has a negative slope and this line is falling. Okay, it's falling as your x increases, y decreases. So to summarize, the effect of changing the value of m on the graph of a linear function, the effect is on the steepness of the line. Okay, so from rising, as you increase it from 1 to 4, then when the slope of the line changes from positive to negative, the line, okay, changes from rising to falling. How about if we change another parameter, which is the y-intercept? So in the equation y equals mx plus b, following examples, we will be changing the value of b. And let's see what will be the effect of this change in the graphs of the functions. Okay, so we start with our parent function. Our parent function y is equal to x. Okay, notice that for all these three examples, okay, our m are the same. M is 1, the slope is 1, 1, and 1. The coefficients of x represent the slope. So all this, notice that the inclination, they're the same. Okay. However, we are changing the value of b, or the y-intercept. So in this case, we have, okay, let's see. I have here plus 0. It's understood to be plus 0. And, okay, plus 0 here, plus 3, and minus 1. So we change this value of b, or the y-intercept, from our parent function y is equal to x. Okay. So this first line is the line representing y is equal to x. This is the same as the original parent function we had in example 1. Next, if we move, or if we change the value of b from 1 to 3. So in the blue line, when x is equal to 0 and y is 0, notice that this point on the y-axis has been moved 1, 2, 3 units up. Any point okay, here is moved 3 units up from the blue line to the red line. So the +3 here represents the movement of the graph of y is equal to x 3 units up. 3 units up. And in the third line, okay, which is the line y is equal to x minus 1, where the y-intercept is -1. So the effect of changing this parameter is a movement of the parent function here, okay? This point here, or any point on the blue line, will be moved 1 unit down. So notice it's moved 1 unit down. So for any change in the value of b, it corresponds to a displacement. So if it's positive, the graph will move up. And if it's negative, the graph, the parent function, will move down. Okay, process the information. You can take down notes. And if we graph all the 3 lines in one coordinate plane, again, our blue line is the line y is equal to x. The green line is y equals x minus 1. And the red line is y is equal to x plus 3. So this is the beauty when you put all this on one coordinate plane, so you can see the movement of the parent function. So notice that we have y equals x, okay? Y equals x. So y equals x. Then the red line is y equals x plus 3. Even just looking at the equation, notice that there is a +3. So we expect the line to be moved 3 units up. So from this point here on this blue line, 0, we move 1, 2, 3 units. Any point on the blue line, if we consider this point here, we move 3 units up. 1, 2, 3. You will land on this point. So take another point down here on this blue line. Let's see, 1, 2, 3. So any point on the blue line will be moved 3 units up. In the same manner, when you have y equals x minus 1, any point on the parent function y is equal to x will be moved 1 unit down. That is your y equals x minus 1. See the transformation from y equals x to y equals x minus 1. That means move each point on the blue line 1 unit downwards. So 1 unit down, 1 unit down. This blue line moves 1 unit down on the green line. Okay, you can write down the summary in your own words. What happens when we change the value of the y-intercept? How will the graph compare to the original or to the parent function? Okay, so the effect again is the movement, the displacement of the graph upwards or downwards. So in our next lesson, we'll discuss the effect of changing the parameters on quadratic functions. So I want you to do some practice ahead. Google Desmos graphing calculator, and on the equation bar, type these 3 functions and see how the graphs compare or how they differ from the parent function. What is the effect when we change the value of a here, which is 1 to 1/3, then to 3? So that concludes our session for today, and I hope to see you next week.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
I chose manual because it's challenging and fun, and it can help me with college.
I chose manual because I wanted to get a jump start in my career with culinary arts.
I chose manual to acquire skills I'd use in real life.
I chose manual because I want to be an ER doctor, and being an EMT is my first step.
Kickstart your future today at Manual Career and Technical Center. Manual is open for all 11th and 12th grade students in both Kansas and Missouri. Learn more today at enrollkc.org/manual or call 816-418-5200.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists, and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.
I love Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything. We are Southeast. Southeast. We stand shoulder to shoulder.
Join the Southeast family. Enroll today.